Hello, welcome to another episode of Xar Talk Show. Today we are going to code Wolfram language on plane tilings, mathematics, geometry topic. So you see, this is a Wolfram language Mathematica notebook that creates tilings, the decorative patterns. There are many aspects of tilings. You can think of it as the mathematical aspect of decorative tilings. For example, this Islamic styled, tiling kind of windows pattern or ceilings pattern, Islamic church pattern. So, and there are, these other symmetry graphics. And these graphics, for example, you will often see in Christian church. So mathematics as mathematical aspect of tilings and patterns, okay? So this is a package I wrote back in 1998, 1997. And I'm going to work on it, going to update it, after 20 years, lots of changes in Wolfram language. So mathematical tilings and geometry, I'm gonna code today, so it's probably just gonna be boring for you. And so for example, here is another of my website where I, so these tiling patterns, okay, let me show you some example. Chicken wire, okay, these tiling patterns, okay, some examples of tilings and patterns, beautiful. Can you see me? If you are here, say hi, okay? So I'm just gonna code it, and it's probably be boring, but I'm going to explain the things what I do, what I'm going to do. So if you are interested in mathematics, in geometry, in the tiling subjects or patterns, symmetry, and if you are interested in mostly Wolfram language, Mathematica, you might find it interesting, learn a thing or two. So some more tilings. This is kaleidoscope. I don't know if you guys, younger people, have seen it. Kaleidoscope is a toy you can twist, and you can see this kind of four-fold symmetry patterns. Okay, made out of mirrors, 3 mirrors, like arranged in a triangle fashion. So you can twist it, and you can see kaleidoscope. Okay, in fact, I haven't seen a kaleidoscope for a while. When I was a kid, 30 years ago, 40 years ago. This is juice and wine, juice and red wine. So this is tiling and patterns. Again, this is kind of like Israel star and the more Islamic kind of patterns. And this is a modern one, Islamic patterns. Okay, and another Israel star pattern. And here is there's a name to this pattern actually. Let me show that. Okay, so tilings and patterns, and here is all the others you can see. So let me show you a picture about that. Okay, so here is also interesting. This I got somewhere. But anyway, let's go back. I want to focus on the code. Okay, so this book I highly recommend. This is the best book on tilings and patterns. Very rigorous, mathematics based. Okay, this is like the book. Okay, the tilings and patterns by the mathematician Grunben and Shepard. When I was younger in the 90s, I actually emailed them. I think maybe email. I emailed them, and they sent me a bunch of publications. They are publications in mathematical journals, because I had some questions. So, when I was younger. So you guys, younger people, go out and do whatever you want to do. Okay, make your life rich. Be a mathematician or be a professor or whatever is your goal. Be a great programmer or whatever. Don't waste time. Don't do memes and stuff. social network. So anyway, Tidings and Patterns. This is the best book. I recommend you buy it. It's out of print, but the Dover publication published it again. So it's on Amazon now, I believe. Let's see. Yeah, so 34, fairly expensive. Let's see, hardcover. Tidings and Patterns. Yeah, okay, so this is somebody else selling their copy. Anyway, so I highly recommend this book. Okay, you go out and buy it. Okay, let me post my website. If you are here, say hi. Okay, I love to hear you. Tidings and Pattern book. Let me post to the chat. Hello, Uyghur. Okay, so Tidings and Patterns. I recommend this book, and let's see what else. Yeah, so I wanted to show you. That particular. Okay, so let me show you some of these things related to tidings and patterns. Okay, so open that. I already showed that. Open that. So it's been 30 years, and I've been now working a lot on Mathematica, on Wolfram language. Some of these are extremely beautiful. Okay, so let me just go over and introduce you some of these tidings and pattern, the mathematical aspect of it. Okay, so let's see. So this is one of this is more serious mathematics I wrote in 1997 on discontinuous groups of rotation and translation in the plane. This page actually got cited by lots of academic publications, journals, or in workshops, back then. So this is about 1997 I wrote this article. So theorems on rotation and translation. So the subject of this page is about groups. So group theory, that's part of abstract algebra. Okay, so yeah, I recommend that you read this. So it gives you a taste of what is abstract algebra if you haven't encountered it yet. Typically, group theory, abstract algebra, if you are an engineer or physicist, you are not likely to learn it, But if you are a math major, if you are studying math to become a mathematician, a math major in university, you typically study group theory in your third year of college, which is usually after calculus, after multivariable calculus, after introduction to differential equations, and after linear algebra. So usually after you have linear algebra, then you will have a course on modern algebra, also known as abstract algebra or simply algebra, as opposed to high school algebra. High school algebra is like you solve equations, x squared equals to 3. What is x? That's high school algebra. But which belongs to the proper, algebra. But anyway, abstract algebra, which is what you study when you, after you study linear algebra. Linear algebra is like a part of it. So anyway, so let me show you some. So this, for example, why is it related to tidings? You can see in this picture, this is a classification of symmetry of any possible wallpaper patterns. Okay, so you classify, for example, you see this pattern is reflection. So you can see the red lines are reflection lines, and this pattern is reflection, both horizontal and vertical. And you also have rotational pattern, like right here. So you rotate fourfold rotation. So every time you rotate this wallpaper 90 degrees, it becomes 180 degrees, it becomes itself. So you have twofold rotation. So then, so there are several others. So, these are all possible symmetries And this, in mathematics, we call these wallpaper symmetries. So, and the more beautiful ones are six-fold rotational patterns like these. Okay, so for example, we actually encountered several of these. So you go to a random one. So this is six-fold rotation. This is four-fold rotation. So anyway, so all in all, there are like 17 possible of them, 17 possibilities. Okay. So anyway, so these are some of the examples. Yeah. So let me show you. Let me show you the. Okay. So this and then we have wallpaper gallery. Okay. So this page shows each one of these 17 possible symmetries, wallpaper symmetries, using only one single motif, that is one single pattern, the star, the pentagonal, the 5-pointed star. Okay, so you can see the background image is a wallpaper, and this embedded image shows you the symmetry, illustrate the symmetry of this wallpaper. So in this example, you can see you have vertical symmetry of lines. That's called mirror symmetry or reflection, meaning that if you reflect the line in any of these any of this line, the wallpaper becomes itself. So you have reflection symmetry, any vertical line. You also have that for horizontal lines. And then you have a fourfold symmetry, like right here, like in the center. So meaning that every time you rotate around that point 90 degrees, the whole wallpaper becomes itself. Rotate again 90 degrees, the whole wallpaper becomes itself. So fourfold rotational symmetry. Then some other point you can see over, let's say where is that? Over here. Okay, for example, over here, you have a twofold rotational symmetry, meaning that at that point, you can rotate the whole paper around that point 180 degrees, then it becomes itself, but not 90 degrees, okay? So you see, some of these points are fourfold symmetry, some other points are twofold symmetry. So that makes it, quite interesting. So let's see, let's go to the next one. This is a bit more complex example, and you have fourfold symmetry and twofold symmetry, and the most beautiful one begin with threefold symmetry, like this one. So you can see at each point, many points, here, here, you have threefold symmetry. That means you rotate 1/3 of a circle, the pattern becomes itself. Okay, so this is again wallpaper symmetry. So you can see this wallpaper is kind of simple. So at any of these triangle points, you have threefold symmetry. However, you do not have rotational symmetry. I mean, you do not have like the mirror symmetry. Like there's no line anywhere on this wallpaper that you reflect it, you mirror it, it becomes itself. There's no such. So this is purely threefold symmetry, so that's, and using the star as the motif. Very interesting. So let's look at next one. Can you press arrow? No, okay. So again, so this is like before. You have many threefold symmetries, like over here, over here, over here. Many threefold symmetry. But this one, you also have reflectional symmetry. For example, along this vertical line, you can reflect it, it becomes itself. And then you have also you have several such lines. Okay, so very interesting pattern. So these are about wallpaper. So if you want to look up Wikipedia, search for wallpaper groups. Okay, wallpaper groups. You see, Wikipedia, back then there's no Wikipedia when I wrote it. So, but Wikipedia has become, over the past 20 years, literally 20 years. Wikipedia began in 2003. So Wikipedia become very rich. So you can learn what is this wallpaper group, what is it about? Why is this like a simple, carpet pattern have so much mathematics? This is about group theory, okay? There's so much mathematics in it. And group theory is one of the foundational, very important mathematics, one of the most important. Every mathematician, doesn't matter what field, you have to know group theory, okay? And the wallpaper groups is one of the best example to learn about this group theory. Okay, they used to cite my website. I don't know if they still do. They don't anymore. But I think they used to, cite Xali, but but Wikipedia, after so many edit, they copied your information and they replaced, and the citation is gone. But anyway, they did a good job. So So okay, so that's about wallpaper. Let's go back to what other things. Let's go through this, and then I'm gonna start to talk. Okay, yeah, let's finish this few more. So anyway, okay, that's okay. So you can check it out. So next, these are about plots of trigonometry equations. Okay, very interesting, but it really doesn't have anything to do with today's subject about tilings and patterns. Okay, but anyway, so for example, this plot is this equation: tangent times tangent and tangent sine x divided by x times tangent, and argument is tangent times y. So very interesting. Okay, let's see next. So we were talking about this package, which I'm going to work on today. Let's see. Yeah, so some features. Yeah, so next, this is another interesting thing, but okay, this has something to do with our topic today, which is patterns. Okay, so this pattern is got a rotational symmetry at the center, somewhere in the center. It's like a Tai Chi, but hexagonal. Okay. So anyway, yeah. So yeah, okay, yeah. So for example, this pattern, you kind of get the wave pattern. You can see kind of wave going out. Okay, that's interesting. And this is a fisheye pattern. So what happens to how do you generate them? So you start with a symmetric pattern, a carpet pattern, then you apply a function that makes it like a wave going out. And similarly for the fisheye, so you begin with a picture or photo or whatever, your face, then you apply a function, which is this function, okay, in Wolfram language. You apply that function, then it becomes a fisheye lens, okay. So that's geometric. All these are geometric transformation. Yeah, so you typically, when you learn mathematics, it's very boring because if you have a good teacher, then it's not boring. But usually they don't talk about. But usually the teacher is not too. Half of the time, the teacher is not too good, so you don't really learn about these beautiful, interesting things about mathematics and geometry. Okay, next. So we talked about this before. So here is another interesting. This is about transformation. So this picture, for example, you begin with a grid, just rectangular grid. Then you apply the transformation or rotation. But this rotation transformation is such that, when you given a point, so when it's near the center, it rotates a bit. But when the points are far away, the more further away from the center, you do more rotation. So this is kind of, so then you get this picture, okay? And the function to do that is here, okay? And this, okay, yeah, so, and here is another transformation. This is almost like a black hole. Sometimes you see, scientific educational program, they'll show photos, they'll show, images, something like that, kind of illustrate a black hole. So how is this one done? This one is similar, but reverse, kind of opposite of that. So the more close to the center, the more rotation you do. Okay, so if the point is further away, you don't do rotation. If the point is further outside of a limit of a radius, then you don't do any transformation at all. So within this circle, in physics, usually it's called horizon, something, event horizon, something. So within this circle, once you pass the circle's perimeter, then you get sucked in. So geometrically, what you do is that if the point is outside of the circle, don't do nothing. But if it's inside the circle, then the closer it is to the center, you do more rotation to it. Okay, so that's how you generate this picture. And that's a description in English. But the interesting thing, if you are into math, is actually trying to do this, trying to draw this. Then you get into coordinate and formulas. That gets you really start to learn things. Okay, so I recommend. So you do it. You can do in your favorite language, Python or whatever, with a graphical environment, or I can recommend, of course, my own tutorials. Just search for Sali Wolfram tutorial. You can do it in Wolfram language. Here's how you can download it for free. Okay. Okay, so let's go back to what we want to talk about. Let me finish, then we're gonna start to code. Okay, some of these, interesting graphics. Okay, now this is the wave transformation like we talked about. You can see it clearly when it's a grid. You begin with a grid, then you apply the transformation. And here is another one, which this is like the fish lens thing. This is like the fish lens transformation. Okay, and a different one. Both of them are like fish lens. And this is a complex inversion, very interesting. Okay, so anyway, so now let me let's go on to the next topic. Any comments? Smart guy, hello. The dude, this would be cool to implement in a game engine for Godot or Unreal Engine. Yes, exactly, and I hope someone does that. Exactly, they would be beautiful in games. With some creativity, you can create games. One of the trick about let me digress a bit. One of the thing about creating 3D games with these ideas is that usually you don't want to directly just focus on the image. If you just show the image in a game, like, what does it do? Like, people are not interested in this. Yeah, okay, that's pretty, and I mean, that's what does it do. So what you want to do in a game is that you design the gameplay or the map, where you can run into, or with these ideas. For example, this black hole idea. So certain area, if you enter it, then you there's some kind of gravity that sucks you in. That's how you implement this kind of idea. You don't want to just like show this picture that that what does it do. So you design a puzzle. You don't even show. Okay, this is a circle. If you enter it, something. You don't do that. But you do have that. You just don't say what it is. Then you have all kind of interesting things can happen. It's about game design. Okay, so let's go next. Now this one is interesting. This I got somewhere from the web. This site, let's see if it's okay. It's Twitter. What? So anyway, this is just like a tiling. This is just like a tiling we showed before. Like one of the two-dimensional tiling, but it's three-dimensional. That's what happened here. You see, three-dimensional tiling. This one is called uniform honeycomb. I'm not sure that's the technical name. It looks like it is. So anyway, in mathematics, you study this kind of thing. You study the symmetry, you study how they repeat. And in fact, this is actually applied mathematics. It's called crystallography, okay? Crystallography. So we can see, okay, you got X-ray crystallography. So you see molecules are arranged, you have seen snowflakes, very common. Molecules are arranged in a pattern. Let's see if they show any interesting ones. So this is very much applied. You have to study, you have to understand, if you are a chemist or if you study material science, how you can make all sort of materials. And, today we have, for example, bulletproof vest or non-stick cookware. How do you make them? And, all this sort of thing. Actually, this page is not it. Let me show you a more appropriate page. Crystallographic disorder. Crystal structures, okay? So, yeah, crystallographic disorder, okay. Crystal structures, okay? So this is like the three-dimensional symmetric pattern. This is how molecules, crystals are bound. So you have to, for example, if you are a chemist, you need to know what are the all possible mathematical ways for points and lines to arrange themselves in three-dimensional space in a symmetric way, because that's required to know. I mean, once you know mathematically what is possible, it helps you a lot in figuring out how the crystals actually, the molecules actually arrange themselves, things like that. So this is mathematics, in particular geometry. You see lots of math, very interesting. So if you want to study this kind of thing, for example, like today, the tiling and stuff I'm talking about, usually you don't study that in college. I mean, usually there's no like one course teach you about this subject, okay? So this subject belongs to geometry, group theory, and symmetry, and tilings and patterns, okay? So mostly belongs to abstract algebra. But if you are a math student, if you are a PhD student, usually you don't even, you don't encounter, there's no course that actually teach you this. You see, because university, they can only teach you so much things, and typically the mainstream fundamental topics, they don't, so even if you have a math degree, you may not have heard of this kind of thing, if you are not doing, chemistry, engineering, and studying crystals, things like that. Okay, so yeah, okay, so I think that's it about these various things, tilings and wallpapers. Okay, and this image is a tiling on a sphere, another variation. So this is Islamic pattern, and this mathematician, I kind of know him a bit. I talked to a Canadian. What's his name? Craig S. Kaplan. Now he's a mathematician. God, dead link. Okay, that link. Let's just search for his name. He's a mathematician who specialized in this tiling and symmetry. Okay, that's his specialization. So if we search, so he's an expert in this topic. So let's see if we can go to his website. Yeah, so this guy, this photo is old. This photo is like 20 years old. But anyway, he's a Canadian mathematician. Okay, very interesting. And apparently, yeah, he's a professor now. Yeah. So let's see what else. So download from language. Okay, not found. Close. Yeah, patterns on a sphere. And here is another interesting variation of tiling and patterns. Now this one is interesting because for two reasons. One is it's fractal. Okay, so it's recursively nested in some sense. Okay, so you have a pattern, but unlike a ordinary pattern, oh god, we have lots of, unlike these just ordinary carpet patterns or wallpaper patterns, they are unusual in a sense that you never seen it before, let's say before 1990s. You never seen a fractal pattern in human history. Meanwhile, the other patterns you have seen, you might have seen, it's possible, these patterns is possible, but fractal is kind of like a new. It's very interesting in a sense that it's a new idea. Like human animals don't know this thing before 1990s, say. So it's a fractal. But also the other thing interesting about this one is that it actually show you the clockwork mechanism. Beautiful. Okay, and there's another one. This is done by, now I don't know who did that one, but this one is done by this guy. Okay, so yeah, very interesting. So let me show you. Okay, so the most popular guy about creating artworks that illustrates the beauty of mathematics is this guy, a Dutch guy, MC Escher. You probably have heard of it. And these are some of my favorite of all his work. I have a collection of his work, a thick coffee book. It's somewhere, I forgot. But anyway, I have, so these three, I would say probably is my favorite artwork of MC Escher out of all his artwork. Okay. And one of my favorite planar one is this one, butterfly. So this one, the pattern itself, it also shows another interesting variation. So you see, you can see it's a symmetric rotational symmetry, fourfold rotational symmetric pattern. But however, as things gets near the center, it shrinked into it. It kind of gets smaller. And this has something to do with you might model it with hyperbolic geometry. Okay, hyperbolic geometry. You can look up Wikipedia. You can find lots of other pictures. Anyway, that's math topics you can get into deeply for. You can get a PhD in hyperbolic geometry and so on. So anyway, so this picture is interesting in that one, it's this kind of hyperbolic thing. The closer to the center, things become smaller. That's one thing. Now the second thing, very interesting and unusual about this artwork, is that if you look at the pattern, if you study the pattern closely, okay. So let's open it. If you study the pattern closely, you can see that they, the circle, you see these 4 red circles, then you have these 4 yellow circles. you can kind of see some sort of symmetry, how these colors are arranged. You see there's a blue circle here out of all these butterflies. You see yellow circle, red circle, yellow, red. Then on the outer one you have green circle, then you have blue circle, then you have red circle. Oh wait, green, blue. So it's cycles: green circle, blue circle, green circle, blue circle. Then if you go outer, you have red circle. Let's see, red here and yellow here. Okay, and red and yellow and red and yellow. Again, two cycles. So that's, so it's quite amazing how, they color part of the butterfly to create this kind of color patterns. Very interesting. So MC Escher. Okay, so then let's see next. Did you see? Okay, so there's another one. This is also kind of interesting, also in a different way. It's actually, this is a plot of a complex function, okay? But they render it with marbles. So you got, this very interesting by this guy, Doyle, okay? They call it Doyle spiral plus Mobius transformation. Okay, then another thing is tiling and patterns is very much tied to braid theory, knots and braids. So you can see this is a weaving of your clothing. Actually I've been looking into clothing and textiles. Like to a modern man like us, we wear clothes every day, right? Underwear or whatever. But have you ever looked at how is it made? What kind of thing can make this, right? You have cotton, you have silk, you have, or blue jeans, how do they, cotton is kind of a plant, right? How do you get the pattern into this thing, right? So textiles, that's a tremendous deep topic, the history of textiles. Then you get into knitting and weaving, and this kind of beautiful cable knit. This is called cable. How do they pronounce this word? Knit or night? I always say it night. So anyway, beautiful. So amazing mathematical thing, you see. And then you have this thing. How is it possible? You can see how intricate and delicate and intricate it is, these patterns. And then you have these Chinese knots, patterns and tilings, okay? All these are tilings and patterns related to. And then you have these Celtic knots, which is a kind of Northern Europe Celtic tradition. They draw these kind of things. And then you have this modern rendition, okay? Now this one is interesting, worth commenting on. So this one, so on the overall, on the whole, you can see a pentagonal star pattern, right? That's on the whole. But if you magnify, you can see it's made of links and weaves. It's made of weaves. You see this thread twisting, going around. Very complex, very interesting, you see. And then, how is it made? What is the structure of this weaving? I don't know. So, so weaving, okay, so very interesting mathematical patterns. That's why I find them fantastic, amazing. Okay, then we have this one. This one, like we've seen before, this is pretty common. You can create random ones, and then this animation shows you how it's done. You just have a bunch of squares. On each square, you can draw a pattern, connecting to the sides. Then depending on how you orient the square, you got these, different patterns. This thing is called trunchet tiles. Okay, it's got a name. And then you have a three-dimensional version. Now that was my girlfriend's sleeves in Second Life about 10 years ago, 14 years ago. So we went in Second Life and we built this, and then you have three-dimensional version created by her in Second Life. Second Life is like a virtual reality. Okay, I think I covered all of these. Now it's 47 minutes actually. I was going to code the padding pad, and I was going to code my package, but let me show you. Let's start Wolfram language. But now we already talked about tilings and patterns for 50 minutes. I think I'm not going to code it anymore. Okay, anyone can you start solving millennial price problem on the stream? Are you kidding? To some of you who, I suppose many of you are going to YouTube watching shows, you don't, you are not a mathematician, or maybe you are a math student, okay? So anyway, for most people watching online stuff, they watch YouTube mostly for entertainment, right? Most people. So when you see mathematics, there's quite a lot mathematics YouTube channels. They talk about interesting mathematical things. You have no idea what they actually are. I mean, to you, it seems, oh my God, these people are so smart. It makes sense. They're talking about these things. It makes very smart. There's a three-dimensional space, time travel. Oh Jesus, this or that space, black hole. What happened to black hole? This, that, wormhole. As an entertainer, I mean, as someone going for entertainment, going to YouTube, you find them amazing and smart people, but you don't really know what they're talking about. Like, you have no idea. Unless you are a math college student or physics, study physics, in a college, then you have some idea. This one is good. Tutorial on the nature of black hole. That one is bullshit. Okay, then you can start to tell this one is just pure drama, no content, bullshit. Black hole, this black hole, time travel, shit. Okay, but you can tell if you actually studied some physics, even a beginner, then you can tell this is a good video. It actually teach you what is the black hole or chemistry or So I mean, the point is that if you don't really haven't studied any of these, let's say calculus, okay? If you haven't really studied calculus or group theory, you have no idea what I'm talking about. You just think, oh, this guy must be smart, beautiful graphics, right? But you don't actually know. So you are asking about millennial price. Millennial price. Yeah, I hope I can even understand the problem. Okay, that's the difference between what I know and millennial price problems. Okay, there are about 10 millennial price problems. You guys, some of you may not know. Let me introduce millennial price. Okay, there's a Wikipedia. Okay, there's about 10 problems, I think. Each one, if you solved it, you get 1 million US dollars. Okay, actually that's pretty small, because if you are the someone who can actually solve this problem, you are worth more than 1 million. Okay, people want you more than 1 million easily. Okay, but anyway, any one of this problem, you got 1 million problem. Okay, now let me tell you how I understand, so you can see, you can get some kind of context. Okay, this level of mathematics, this level of programming, if you don't know anything about it, you think it's all over your head. But if you really actually just know a little bit, you can tell there's different levels, okay? So the millennial price, I can tell you, of all these 10 problems, let's just say 10, I don't understand 8 of them. Like, I don't even know what they are asking, okay? And if you want to understand, just simply understand what it is that they are asking. Takes you like 4 years, okay? 4 years to understand them, okay? Like, okay, let me explain. Poincare conjecture, okay, that's one of them. Birch and Swinnerton-Dyer conjecture, I have no idea about that. Navier-Stokes existence and smoothness, okay? Go solve it. You get 1 million. P versus NP. Now, as a programmer, I'm a programmer. I'm more of a professional programmer, okay? Now, a lot of people might have heard of this, P versus NP, and it's kind of dramatic, but most people have some idea what it is about. But it acts for me, or for example, I don't. You have some idea what it is about, but it comes to the question of, do you really understand what it is asking? Most people don't. I'll say I kind of know, but not really. Okay, so I understand kind of what this problem is asking. But if you push me, I cannot be precise. Okay, all of these problems are very precise. Okay, you can write a mathematical equation like that says, that can show you what you understand. Like, give a concrete example. So this one, P versus NP, I kind of understand. If you push me within a month, I can truly understand it. Within a week, okay, like I spend 3 hours a day, I can start to tell you, and I can teach you what this is problem, exactly what it is about, okay? Not just with vague idea. Oh, P just means polynomial time. NP means non-polynomial. So some problem are polynomial. Can you use it? Then, like hand waving. Most programmer, 99 out of, let's say 1 in 10,000, I would say 1 in 100,000 actually understand this. You won't unless you actually, read it. Anyway, so next problem, right? Riemann hypothesis again. Again, I understand the problem. The problem is find the zero. Let's see. Prove that all zeros of this function lies on a line, something like that. The Riemann zeta function is a function whose arguments may be any complex number other than 1, and whose values are also complex, okay? Its analytical continuation has zeros at the negative even integers, okay? Negative even integers, -2, -4, -6. When you give these numbers to this function, the result is 0, okay? That's what it means. These are called its trivial zeros. However, the negative even integers are not the only values for which the zeta function is 0. The other ones are called non-trivial zeros, okay? Now, the Riemann hypothesis is concerned with the locations of these non-trivial zeros, okay? So in other words, you are given this function. You want to find, this function we know, if you give it -2, -4, -6, the answer is 0, okay? But however, there are some other numbers, like shown in this graph. There are some other numbers that the output is also 0. The problem is, prove the real part of every non-trivial zero of the Riemann zeta function is 1/2. Okay, so the real part, let's see, the real part, yeah, so basically it's saying that you have to prove that every 1 over 4, every 1 over 2 of a complex number whose real part is 1 over 2 may be, okay, it's a bit complex to phrase. It's saying that all these other zeros that makes this function 0, the input for the function that makes it 0 is such that the real part is always 1 over 2. Okay, so you have to prove that. Now, yeah, so I kind of understand the problem, but you take a deeper look into what is this function? You can't even fathom. Okay, this function is a zeta function. The input is s. Okay, s. What is the output? The output is that, so you sum these numbers, so 1 over 1 raised to s power plus 1 over 2 raised to s power plus 1 over 3 raised to s power to infinity. Okay, that's not too hard. Yeah, but so you have to sum this infinite sum. Then whatever you input as, then whatever output is a result, okay, of this zeta function. So this zeta hypothesis, Riemann hypothesis, is saying that you want to find all the zeros of this function. Okay, so so if you have studied complex analysis, even a basic one, then you understand this problem, Riemann hypothesis. For example, this one, Yang-Mills existence and mass gap. Okay, I don't understand it. I don't even try, because that's physics, related to physics. Okay, I don't know too much about physics. Okay, Riemann hypothesis, I know a bit. P versus NP, I know a bit. Navier-Stokes, that's another physics thing. I have no idea what it's about. Usually differential equations. Okay, Hodge conjecture, I believe that's algebraic variety, very deep topic. It's mathematics, pure mathematics, but I have no idea. Like, it'll take me a few months to just vaguely understand what's it's asking. Okay, that's what I'm saying. So when you look at things you don't know, usually you have an impression. Oh, that's, for example, juggling. Okay, let's talk random. And that's it for today. Thank you guys for watching. Xali juggling. Okay, I have a page on juggling. Let me tell you something about it. Okay, here's my favorite juggling balls. Now, so ball juggling, I have collected many videos about juggling because I was into juggling. So many of these are the great, juggling I have seen. I've seen a lot. I've seen basically all possible. So anyway, some of these are great. So, do you juggle? Okay. So if you never are in the juggling community, you don't know anything about juggling. So all you see, most frequently question is, how many balls can you juggle? Right? You don't know. I mean, that's like the common question. How many balls? How many balls can you do? Oh, 5, 6. This is better because it's got more. 6, right? Then, but this 3-ball juggling. Okay, this 3-ball juggling is far more difficult than 6 balls. Okay, this guy, Victor Key is one of the top juggler. Okay, he works for Cirque du Soleil. Used to, I don't know about now. Juggling is like sports. When you get old, you are kind of done. Usually, I mean, it's age. Very much related to age. beyond certain age, you get older, you can do it. So anyway, so juggling. So when you watch juggling when you watch circus, you have unicycle, you have juggling, some juggling balls, some juggling clubs, some do a chainsaw. That's the most idiotic, chainsaw and the apple and the bowling ball. Okay, but you have no idea. It's more difficult than the other. You have no idea. To you, when you see a chainsaw, oh my God, that is the most difficult. But you have no idea. You don't know. Only when you actually spend time, a week, a month, to juggle, to get into the community, then you know right away which one is actually the difficult. Okay, which one is just drama for show, gets the most applause, the most dramatic, the chainsaw and apple, the idiotic shit. Same thing for mathematics, okay? That's what I'm saying. Same thing for mathematics, same thing for programming. Like many of you are programmers, right? You get people asking you, can you fix my Windows? My Windows got this problem, can you fix it? That's it for today. Thank you guys for watching. Okay, so let me show you the package. So this is the source code for the package. That's it for today. No, let's show the gallery. Okay, so this is the Wolfram language code. Okay, so oh wait, no, this is not the package I'm talking about. Oh yeah, so tiling and patterns. Okay, so we gotta, no. So plain tilings. What the fuck? Okay, let me show it, and that's it for today. Okay, so this is the tiling package I was going to code today, but we already talked for an hour, so that's it. So let me just show it so that at least that we get something to run. I need to do a backup first. Okay. Any comments? Okay, so I need to load the package. So here is the source code for the package. Open it in Wolfram language. So here it is. So here's a code. Those are documentation, and OBS Studio connected. Okay, got a little problem. Okay, but that's it for today. Thank you guys for watching. If you like my stuff, PayPal me, okay? Go to xali.info. xali.info. You can see my website. Then all the way down, there's my Patreon, Amazon gift card, PayPal, or you can buy my Emacs tutorials. I had some delay in sending out Emacs tutorials. Few people bought it, but I did send out. So my Emacs tutorials or my JavaScript in depth. Okay, thank you guys for watching. Bye. Fantastic. After 20 years, still works. Let's see, there's some beautiful ones. Okay, that's an illustration of symmetry groups. Okay, then this is an illustration of the kaleidoscope fundamental region. This region is called fundamental region because by having this region, you can create a whole pattern by just symmetry. Okay, so let's run it. Let's see if that works. Oh, it does. Okay, the graph is a bit more different. Let's see, magnify. Fantastic. And here is some random pattern. Oh, it works. Random pattern. So that pattern and this pattern has this symmetry. Okay, but why is it black and white? It's supposed to be color. That means I need to fix it, something. I think it's supposed to be color. Okay, let's see what's more interesting. So here is a hexagonal grid or triangular grid. Here is a square grid, but with a pattern, a certain symmetry on the coloring of the dots. And here is another hexagonal grid. It's like a triangular grid, but variation. Okay, here's some patch weaving. So we started to do some weaving, some Islamic patterns. Let's run it. Kind of snowflake patterns. Okay, honeycomb. Then a very interesting arrow thing. Here's a code. Let's see, we can make it code into mathematical typeset. And then, okay, that's it. Bye.